Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you all to this live session. This week we are going to cover fluids, okay, and we will be having total of 6 lectures, each lecture being of 1 hour, okay. So let me share my screen with you people so that we can start without losing any time. Okay, so let's start. So this week's topic is fluids, and the study of fluids can be divided into two broad categories. One would be fluid statics and the another would be fluid dynamics, or simply fluid statics is also sometimes known as hydrostatics and hydrodynamics. Okay, so in fluid statics we will be studying about the variation of pressure or behavior of the fluid, okay, which is kept inside a container and which is static. The fluid should be static with respect to container. So that part we will be discussing under the heading fluid statics. Whereas if the fluid is flowing, okay, inside some pipe or somewhere, so that discussion we will be doing under the topic under the heading fluid dynamics. Okay, so let me very quickly cover like what small portion we will be covering under these headings. Okay, so in fluid statics, firstly we will be talking about hydrostatic pressure. We will talk about Pascal's law. And once we have defined hydrostatic pressure, we will be like looking at its variation of pressure inside liquid. Okay, and we will be looking at some pressure measuring devices, for example barometer, which is used to measure atmospheric pressure, or manometer, which is used to measure gas pressure inside some container. Okay, so these are pressure measuring devices, and we will look at force exerted by fluid on bodies in contact. Okay, and the another thing, like we will be talking about Archimedes principle, that is very important. Okay, and under the Archimedes principle we will be looking at several things, like we will also look at center of buoyancy, and we will also look at what is the concept of meta center, and we will be looking at equilibrium of floating bodies. Okay, we will be looking at its translational as well as rotational equilibrium. So these are the portions we will be covering under the heading of fluid statics, whereas under the heading of fluid dynamics we will look into the equation of continuity. Okay, and we will be looking at thrust force exerted by incoming or outgoing fluid. So let's say fluid simply, right? Then we will be looking at this Bernoulli's principle, which is nothing but work energy theorem applied over some segment of fluid. And we will be looking at different application of Bernoulli's principle, like for example we will look at the concept of efflux velocity. Okay, and we will be looking at the siphon tube, and we will look at Venturi meter. which is a device used to measure the flow of fluid in a pipe. And then we will talk about dynamic lift, which is governed by the Magnus effect. And we will look into the concept of atomizer, which is very important in the perspective of JE Advance. Okay, so this is the plan. This is the, like, these are the subtopics which we are looking to cover this week. Okay, so in today's lecture, we are going to start with hydrostatic pressure. Okay, so let's first define the pressure. Let's say there is some liquid. Okay, and for the sake of simplicity, let's assume the density of liquid is rho, and liquid is homogeneous, so rho will be constant. And inside this liquid, let's assume there is some body of some random shape is submerged. Okay, so at this boundary over here, the liquid will be in the contact of this body. Okay, so here what liquid will do, it will apply contact force. Okay, and this contact force will mainly be compressive in nature. It will compress, the liquid will exert compressive force, okay, from all around on this body. And this compressive force, you must see, is everywhere perpendicular to the instantaneous surface over here, you must see. Okay, so you have to always understand, like, this force is going to be compressive in nature, as well as it would be immediately perpendicular to the surface over here. So let's say, in order to define the pressure at a point, okay, what we need to do is, for example, if we want to define the pressure exerted by the liquid at this point, so what I must do, I must take a very small area dA over here, and let's say this dF is the perpendicular force. Okay, then the pressure would be defined at this point as dF by dA. Always understand, pressure we can define at a point. Okay, and here at this point, this dA area is very small, and this dF here is perpendicular force. So this is how pressure is defined. So its SI unit will simply be Newton per meter square, which is also known as Pascal. Okay, so this is how pressure is defined. So if pressure at any point is known, we can also find out the perpendicular force experienced at that point. So that is simply going to be PdA. So basically I just have rearranged this expression over here. So that is pressure due to fluid at a point, and this is the force due to fluid at that point, okay, or over a small area dA. That is always compressive in nature, that I have already said. And one more important thing I want to add over here, like, see, so this is the boundary here, okay, which divides the region of this body and fluid. So fluid exerting some pressure on the surface. Okay, so at every point on this surface we can define pressure. Okay, the pressure, there would be a pressure profile on the surface of this body. Okay, and that pressure profile is due to the liquid, and it will not depend upon what is this body over here, what is this body made up of. It can be made up of, like, may be stone, it may be made of a gold, silver, or whatever material it could be made up of. It could be made up of liquid itself. You can imagine the same liquid. So whatever this material is, this pressure profile which has been created by the liquid outside is not going to change, and that concept is very important when we are going to discuss for what would be the force exerted by the liquid, and that is only going to depend upon the liquid only. Okay, so this is how we define hydrostatic pressure. Okay, and now let's talk about the pressure variation in a liquid. Pressure variation in a liquid. Say we have a container, okay, and some fluid is filled inside it, and let's say its density is rho. So under the heading of a fluid static, what we will be assuming that this liquid will be in some container, and this would be static with respect to container itself might be moving or accelerating as well, but this liquid with respect to container is going to be at rest. We are going to deal with all those situations. Okay, so the first specific case, like the first case will belong to when the container is at rest, or you can say moving with a uniform velocity. In other words, you can say the container itself is non-accelerated. So there must be liquid. If there is liquid inside it, is two things we need to understand. So first thing is, if we have 2 points, let's say point 1 and point 2 at the same horizontal level. Same horizontal level means we are assuming that the gravitational acceleration g is vertically downward over here. Okay, so if we are having 2 points at same horizontal level, and whatever may be the distance between them, we can very safely say that the P1 will be equal to P2, or you can say the pressure difference. Let's say the pressure difference over here, that is P2 minus P1, is gonna be equal to 0. So there must be no pressure variation between 2 points if they are at same horizontal level. Okay, at all those points. Okay, these points will be having same pressure. Okay, and now let's look at if the points are have at different vertical levels. Let's say this is point 3 and this is point 4, and let's say the distance between them is say some delta y. Okay, so we must understand, like first of all, P4 will not be equal to P3, and let me tell you, P4 will be greater than P3, like where the pressure will increase in the direction of G. Okay, so in that case, the pressure difference, okay, that would be P4 minus P3, that would be equal to rho G delta y over here. Okay, and see, like we need to understand like how we are getting this result. So this result is simply based on the equilibrium of the element of liquid which is contained between these 2 points. So let's say, let's take a cylindrical element of liquid which is contained between point 3 and point 4. So just considering the equilibrium, so this segment is of the same liquid, and we can assume it to be in equilibrium. So let's say the pressure at the topmost surface is P3 and the pressure at the bottommost surface is P4, and the area of cross section is, let's say, dA. So as we have said, like liquid is going to exert the compressive force. So liquid will be exerting force in upward direction from the bottom. So that would be, and its magnitude dF will be pdA, we have already studied. So that is going to be P4 times dA, and the here the pressure is P3. So the remaining liquid is going to exert compressive force, that would be P3 times dA. Okay, so only I am considering the vertical forces, because the horizontal forces are anyway balancing each other. Okay, so this is P3D, and apart from that, this thing will experience the weight of its own. Like this element of liquid will experience its weight, okay, which will be in vertically downward direction, and that weight here is going to be mass times g, and its mass is going to be, like, rho is its density, and this is of cylindrical shape, so that would be cross sectional area into height, so that would be dA into delta y will be its volume. So this is mass into g. So just doing the force balance, we can very well say that P4 times dA minus P3 times dA is going to be equal to rho g delta y into dA. And you can very well see that this dA thing is getting cancelled, and we have got this relationship P4 minus P3 is equal to rho g delta y. There is one another convenient way of writing the pressure variation equation, and this I am telling you in the very beginning, and that is going to be applicable in all sort of situations, and that equation is simply dP. That would be small pressure variation between 2 points. That would be simply rho times G effective, okay, dot dr. Okay, rho g effective dr. So like if we will be learning like how to use this expression. Okay, like this simply says like pressure will increase if the displacement is along the direction of g effective. Why I have written g effective? Because this container might be accelerating. In that case, the value of g effective might be some other than g, and its direction might need not be vertically downward. Like in this case, g is vertically downward, so this formula will simply turns out to be rho g effective. So rho g dot dr simply, so g is in downward direction. So if displacement is also in downward direction, okay, so then the dot product of g and dr would be simply g dr. Okay, and so that would be a positive quantity. So in the direction of g, the pressure dP will be positive. Change in pressure will be positive, means pressure will be increasing, you can say. Okay, so this is one relationship over here. So with the help of this pressure variation in a non-accelerated fluid, we can say, okay, we can use some concept of pressure measuring devices. The pressure measuring devices work on this principle only. So let's first of all talk about barometer. Barometer is an instrument or a device which is used to measure atmospheric pressure. Okay, so like our atmosphere, you see, is made up of several gases which can also be treated as fluids. So we are surrounded by fluids from all around. Okay, the earth is surrounded by fluids. So that fluid, which is atmosphere, is going to exert force on the surface. Okay, and that perpendicular force per unit area would be defined as pressure at some point. So we are looking to measure that pressure exerted by, or pressure due to, the atmospheric fluid. Okay, so what we are going to do, um, atmospheric pressure is everywhere. Okay, so the way to measure it is simply, the setup of barometer is, let's say we are having a container and we are having a narrow tube. Okay, and in this container we fill mercury, and this mercury rises in this narrow tube, And here what we ensure that there is vacuum. Okay, in the design of barometer we have to ensure that this part of the narrow tube has to be a perfect vacuum. Okay, and the surface of liquid, let's say here this surface of liquid here is exposed to atmosphere. So whatever surface of liquid will be exposed to atmosphere, at that point the pressure is going to be PATM. And now this surface here of liquid is exposed to vacuum. Okay, so whatever the vacuum pressure is, basically the vacuum pressure will be equal to 0. So here let's say the pressure at this point is going to be 0 over here. Okay, so in order to find out the atmospheric pressure, we are going to use the same result which we have just derived. Like, let's take point 1 here and point 2 here, and let's say the rise in of mercury in this barometric column is equal to H, and H turns out to be 76 centimeter experimentally. So what we can say over here, according to our relationship which we have just derived, the vertical pressure variation, that is P2 minus P1, is going to be equal to rho G H. Okay, and now you see P2, I have already discussed that P2 is going to be PATM. Any point which is exposed to atmosphere will be having atmospheric pressure, and P1 I just told that this is going to be 0, so that is going to be equal to rho GH. So simply what we can say, PATM is equal to rho GH. This rho is mercury, that of mercury, and let me give you one data also. Rho Hg, the density of mercury is 13.6 into 10 to the power 3 kg per meter cube, or simply you can say also 13.6 gram per centimeter cube, whichever way you want to represent. So PATM in SI units also you can calculate. Like for example, let's substitute the value of rho Hg, so that would be 13.6 into 10 to the power 3, and the value of G is nothing but 9.8, and the value of H we have already seen, it is going to be 0.76 meter. Okay, so when we will be calculating this, this would be approximately equal to 10 to the power 5 Pascal. Okay, and that is equal to basically 1 bar, you can say, or like that is also known as 1 ATM pressure. This is another unit of measuring the pressure. So this is the value of atmospheric pressure. One another convenient way of representing this as like just by representing like this pressure is equivalent to uh, how much what length of the mercury column. So simply we can represent it as 76 centimeter of Hg. So whenever we are saying like 76 centimeter of Hg, what we mean is approximately 10 to the power 5 Pascal, or 1 bar, or 1 ATM, you can say. That is 76 centimeter of Hg that has been measured in terms of the length of the mercury column, okay, which it is equivalent to. Okay, so that is how we have used this barometer. The another device which we are going to look at is something called manometer. Okay, and this is a device which is used to measure pressure inside a gas container. So if we have some gas in a container, say there is some gas, so it is going to exert some pressure, okay, on its wall. If we want to measure this pressure, and one thing we would be assuming over here, like the gas's density would be so small, so that the vertical pressure variation which we have just seen will be negligible. Okay, so like the gas pressure throughout the volume of this container, we will be assuming it to be same. Okay, so if we want to measure this gas pressure, what we are going to do, like we will connect it with something called a manometer tube. This manometer tube, you see, is like a U tube, U-shaped tube, you can say. So this is a manometer tube, and what we have in a manometer is some mercury filled in it. Okay, there would be some mercury filled in it. So this liquid here is mercury. So now what will happen? So since this manometer tube has two limbs, okay, so there would be some length of mercury column in each limb. So if one of the limb is not connected with the gas, okay, so both side it would be atmosphere which would be pressing. Okay, so same pressing force both side, you can say same pressure both sides. So in that case, the length of mercury column in the both limbs of this U tube or manometer tube is going to be equal. But now you realize the thing is, the gas now will be pushing from this side, whereas the atmospheric pressure will be from this side. Okay, so whichever pressure would be more, okay, if the gas pressure is greater than atmospheric pressure, it will push more, and then the length of mercury column in the left limb will be less, and in the right limb it would be more because of the pressure difference over here. So this diagram, like you can see that this is for a specific case when the gas pressure is greater than atmospheric pressure. So let's say the pressure here, because this surface of liquid is exposed to gas, okay, the pressure here would be nothing but P gas, you can say, and this part is exposed to atmosphere. The pressure here is going to be atmospheric pressure. And according to our result, you see, this, let's say this height h in centimeter we are able to measure. Okay, so simply what we can say according to our derived result, so P gas minus P atm is going to be equal to, you can say, rho hg into G into H, or you can say the gas pressure is going to be P atm plus rho hg into G into H. Okay, so you can substitute the values and also calculate the result in SI units. And alternatively, more convenient way of representing it is like P atm, we have already understood, like this is equivalent to 76 centimeter of Hg, and this pressure is equivalent to, you can simply say, H centimeter of Hg. So this result would be 76 plus H centimeter of Hg, you can simply say. So that is how we are going to measure the gas pressure. And here I want to discuss one important concept, that is something known as gauge pressure. Gauge pressure. Now you see, the pressure of gas or pressure of anything, like we have assumed here, like gas pressure here is greater than atmospheric pressure. Okay, so let's say this is some absolute scale. Let's say this is zero pressure, and this here is some level which is atmospheric pressure. I am drawing a pressure scale. So let's say some gas pressure we are talking about at this level, like P1. This P1 clearly you can see is greater than P atm, and let's have another level here, let's say P2, and that you can see that less than P atm. Gauge pressure simply measures like how much excess the pressure is to the atmospheric pressure. So this value is basically gauge pressure. So P gauge, you can simply say that would be the absolute pressure minus the atmospheric pressure. Okay, so here you can say at this situation gauge pressure is like P1 gauge is positive, and we can have negative gauge pressure also, P2 gauge, that is negative over here. If the pressure at any point, or the gas pressure, is less than that of atmospheric pressure, in that case, if the gas pressure is less than atmospheric pressure, in this diagram of manometer tube, you will be seeing that uh, the length of the mercury column in the left limb will be greater, and in the right limb it will be smaller. That would be simply giving P gas is less than P atm. So in that case, we will be saying, and using that relationship also, we will be able to see, since P gas would be less than P atm, the gauge pressure would be negative. So it is very important to understand, like whenever we are calculating gas pressure, okay, like we can use, we can, like in this device, basically we are measuring H. So in that case, if the absolute pressure of gas is 76 plus H centimeter of Hg, the gauge pressure of gas will simply be H centimeter of Hg. Okay, here, like this device is measuring only H centimeter. So whatever this device is going to measure, it will be simply giving you the gauge pressure. Okay, it can be positive as well as negative. So this was the concept of gauge pressure as well as the concept of manometer. Okay, so the now next discussion here is, let's do some problem, YouTube problems. Like YouTube simply means a tube which is shaped like the alphabet U. Okay, let's do some simple problems here. So let's say this is some YouTube. Okay, so if a liquid is filled in this U-tube, like I said, the level or length of the liquid column in each limb is going to be same, because from both sides it would be the atmospheric pressure which would be pressing it. Okay, but let's discuss the case where we are having, let's say, two different liquids in this U-tube. Let's say, for example, one liquid is from here to here, something like this, and let's say we have another liquid which is extending from here to here. Okay, and let's say its density is rho1, and see, this length, say, is L1. Okay, and for this, let's say, let's draw a level over here. Okay, and let's say this density is rho2 and this length is L2, for example. Okay, so in order to relate rho1 L1 and rho2 L2, what we are going to do here, we want to find out L1 and L2. If we are able to find out L1 and L2, we will be able to find out the difference between L1 and L2, that is the difference in level of columns in both the limbs. So basic idea is, we are looking to find out the value of L2 and L1 over here. So what are we going to do? So we are interested in applying the pressure variation formula over here. So like for that, like the concept which we are going to use is the the 2 points at the same horizontal level in a homogeneous liquid is going to be same. So for example, 2 points we have to choose. So in this, I'm going to choose this point and this point. These both points we must make sure we are choosing in the same liquid. Like for example, this point is completely in the liquid of density rho2, and this point is at the interface between the liquid rho1 and rho2. So we can apply the pressure variation formula between A and B. What we are looking at, that the pressure at A is going to be equal to pressure at B, because we have already seen that in a homogeneous liquid, the pressure will be same at the same horizontal level. So now what we can say, like what would be the gauge pressure at A. So now looking at this liquid column over here. So this liquid rho 1 will be exerting pressure over here, and what would be that? So that would be simply according to our knowledge. Okay, that is going to be rho 1 G L1. I am writing the gauge pressure only. If I work in terms of absolute pressure, both side we will be having, like in writing PA or PB, we will be having a terms of PATM. But since we are comparing, that term of PATM will be cancelling both sides. So it is always convenient. So whenever we are looking at the pressure difference, we can work with gauge pressure as well, because in pressure difference, in all the pressure we will be having PATM term that would be getting cancelled. So we can simply write rho 1 G L1 is going to be rho 2 G L2. Okay, so that will be giving you like simply rho 1 L1 is equal to rho 2 L2. Okay, so this is an important relationship. So once you have found out the value of L1 and L2 in a given question, you can also find out this H, which would be simply L1 minus L2 over here. So this is one very simple question. One another simple question of YouTube we can have is, let's say we have another YouTube, say something like this. And this time in this problem, I will fill up 3 liquids, let's say, or we can say there was some mercury in it. Okay, and over the mercury there was some oil. So this is say mercury or Hg, and this is some oil which we have put in one limb, and from in the another limb we are filling some, let's say, glycerine. Okay, we have filled some glycerine such that the height of the liquid column in both the limbs has become equal. Okay, and let's say this is glycerine. Let me give you some specification also, that this oil has density, for example, 0.8 gram per centimeter cube, or you can say its specific density is 0.8. And for the mercury, we know it already, that is 13.6 gram per centimeter cube. And for glycerine, let's say that is 1.3 gram per centimeter cube. So this is the thing. Okay, and the height of the glycerine column is given to us. Let's say that is 20 centimeter, and we are interested in finding out that what would be the height of the oil column. What would be this H over here? We are interested to find out that. So what we are going to do, so just like the previous problem, we are going to choose 2 points at the same horizontal level, and we must make sure that those 2 points we are choosing is in the same liquid. So let's choose one of this point. Let's say this is point A, and the another point, let's choose B over here. So both these points we can safely say are at same horizontal level, A and B. Okay, and that is in mercury. Can we choose this point and this point in order to say like the pressure at these 2 points will be equal? Definitely not, because this point here is in glycerine and this point is in mercury. We cannot choose this point, or we cannot choose the liquid at this level, for example this point or this point. No, we cannot do that, because this point here is in glycerine and this point here is at the interface of oil or mercury. So in no way it is in glycerine. So we have to be very careful, like we have to choose 2 points at the same horizontal level. Okay, in order to equate the pressure to be equal. Okay, if they are in a homogeneous liquid or in a liquid with same density, you can say. So simply we will be writing PA is equal to PB in this case also. So the gauge pressure at A is simply going to be, because above it only glycerine is there, so gauge pressure is going to be like, for example, density of glycerine is 1.3 into G into length of the glycerine column, so that is 20 centimeter, and simply PB will be equal to, like from here to here it is oil, so that is H what we have to find out. So that is going to be 0.8 into G into H plus this pressure difference over here, so that density is 13.6 into G into this height would be 20 minus H. So we don't have to worry about units over here, because throughout this equation we are using same units, like the unit of density will be cancelling, unit of G will be cancelling, unit of this length will be cancelling. So we need not worry about the unit thing as long as it is consistent throughout the equation. G anyway here is getting cancelled, so we will be very well able to solve for H. So that's your job. Okay, so these were some problems of YouTube. And now let's discuss one more concept, which is something called Pascal's law. Pascal's law. So Pascal's law simply states that change in pressure applied to an enclosed, incompressible fluid is transmitted to, or transmitted, you can say undiminished, to every point of the fluid. What I mean to say over here, that if you are increasing or changing the pressure at one point of the liquid, that change is going to reflect at every other point of the liquid inside a enclosed enclosed incompressible fluid. Sorry, enclosed, like the criteria is the liquid has to be enclosed, that must be that closed from all sides. Okay, so one simple example here is one something called hydraulic lift, something called hydraulic lift. Okay, so this lift is used to, okay, lift very heavy object with the help of less force. So let's say there is one platform here or one lever over here, and there is another platform at the same horizontal level, and some fluid is enclosed in between these two platforms. Okay, and here let's say we are having some heavy object, let's say we are having some car, okay, which we want to lift, okay, using our simple muscular power. Okay, so what we are going to do here, okay, we are just making sure in the design, like this is A1 and this is A2, so A2 we want to keep it much greater than A1, something like that. So what we are going to do, we will be applying some force F1 over here. So due to application of this force, the pressure at this point will change. Let's say the pressure will change by delta P, and that will be equal to F1 by A1. Okay, so at this point pressure is changing by delta P, and this change of pressure will be transmitted undiminished to every point of the liquid. So the change in pressure at this point here as well be delta P will be equal to F1 by A1, you can say. So like this would be delta P over here. So due to this delta P, this liquid will be pushing it, okay, over here by force F2. And F2 we can simply calculate the extra pressure delta P into A2. And delta P, as we know, that is simply equal to F1 by A1, and that will be multiplied with A2. So just by rearranging this equation, you can say that F2 is nothing but A2 by A1 into F1. Okay, so as we have seen that A2 is much greater than M1, so that will make sure that F2 will be much greater than F1 as well. So just by, the thing is, just by applying a small force, you are able to lift a heavy object by applying a larger force F2. Okay, so that is the concept of hydraulic lift, and that is very useful, okay, in order to lift a heavy object. So this was the concept of the Pascal's law. And now we have studied the pressure variation in a non-accelerated container. So now let's look at the concept of pressure variation in accelerated container. Say we have a container, okay, and this is the horizontal direction, and let's say it is moving horizontally with some acceleration A. Okay, so the liquid, if there is some liquid inside it, so what will happen? First of all, its open surface will no longer remain horizontal. It will become a little inclined. Okay, so our first task here is to we have seen already like the vertical pressure variation. Okay, and in case of the liquid which was not accelerated in horizontal direction, the horizontal pressure variation was equal to 0. So here in this case, like if we choose point 1 and point 2 here, and if we imagine a segment of liquid between this point 1 and point 2, and let's say here the pressure is P1 and here the pressure is P2, so the force here from this side would be, let's say, some P1A, and the force from this side would be P2A. So can we say here also that P1A will be equal to P2A? Is this element here is in equilibrium in ground frame of reference? The answer is no. So with the whole container, this segment of liquid is also accelerating with same acceleration. So we cannot say that P1A is equal to P2A. So what would be the force balance equation? Let's say the distance between point P1 and P2 is delta x. So just writing the equation of force in horizontal direction, that will simply give us P1A minus P2A. That would be mass of this element. Mass of this element would be rho, that is the density of liquid, into A into delta x, that is mass, and its acceleration in the direction of force, or force we have written in the direction of acceleration, you see. So this would be the, and this will get cancelled. So P1 minus P2 is equal to rho A delta x. So that is the pressure variation in horizontal direction over here. So this is P1 minus P2. Vertical pressure variation would be still be rho g delta y, that we have already seen. Okay, so what we can figure out, like the pressure decreases in the direction of acceleration. Pressure is decreasing in the direction of acceleration, like or in other words, like you can say the concept of G effective we have learned. So the concept of G effective is say for example, the G at any element, the G is acting in vertically downward direction, and uh, any element of liquid will be experiencing a pseudo force here also. So like let's say this is mg and this is ma. So the resultant force experienced by this body is going to be in this direction, mg effective, you can say. The value of G effective you are seeing, the value of G effective simply will be equal to root under g square plus a square in this case. Okay, so the pressure is going to vary in this direction, in the direction perpendicular to the direction of g effective. The pressure is not going to vary. So that is another interpretation, that if the pressure at all these points are going to be same, so this line here, sorry, this line here is going to be the perpendicular to the direction of g effective, and that is how we can find out the inclination of open surface of liquid. For example, this angle we seek to find out, theta. So geometrically you can say that this is same as this angle theta, and looking in the geometry, tan theta very well you can say is nothing but a by g. So two things we have understood, like the pressure variation and the angle of inclination of the open surface of the liquid over here. The another way to find out the same thing, like tan theta is equal to a by g, is another, in simpler terms we can find out the same quantity using simply the pressure variation. Let's take 2 points A and B at the open surface of liquid. Okay, so the pressure at A as well as pressure at B both are going, since both these points are exposed to atmosphere, pressure at both these points is going to be P atm. So delta P between A and B is going to be equal to 0. So now let's draw a simple triangle over here, construct a triangle, right angle triangle, and let's say this is some y and this length is some x. Okay, and I will be moving along this path and keeping track of the pressure variation. Okay, so from A to this point, let's say this point is C, so from A to C when we are moving, so we are moving vertically downward direction, so pressure is going to increase by how much? That is going to be rho g y. And from C to B, when I am moving in the direction of acceleration along the same horizontal level, okay, the pressure is going to decrease by rho ax. Okay, and this is the net change in pressure, which we understand is going to be equal to 0. So this simply gives us y by x is equal to a by g, and y by x in this right angle triangle is nothing but tan theta, which would be a by g as well. So two concepts we have learned. Okay, like the pressure is going to vary in the direction of acceleration of container also, or effectively you can say the pressure variation would be in the direction of g effective, and open surface of the liquid is going to be perpendicular to the direction of g effective. We are going to use this concept in order to solve many other problems. Like for example, one specific problem I want to discuss over here. Let's say, for example, there is an inclined plane. Okay, and say there is a container which can slide on this inclined plane. So let's say, for instance, it is sliding down the incline and there is some liquid filled in this container. I want to draw some reference line. Let's say this is the reference line, okay, which is along the incline, and let me draw another reference line, sorry, another reference line. Let's say this reference line I have drawn, that is along the horizontal. So I am interested in finding out like what would be the shape or what would be the inclination of open surface of the liquid inside the container. Means I would be looking to how much angle will it be making from the green line over here, which is the direction of incline, or how much angle will it make from the red line over here, which is the horizontal. So in order to do that, so I will take a molecule or take an element of liquid, okay, on the open surface of the liquid, and I will simply do the force balance. Okay, so let's say this is an element of mass m which is at open surface. Okay, and let's take, this is the direction of incline. So this is experiencing basically a force mg in this direction. Okay, that is its weight. And apart from that, since it is in accelerated container, so with respect to container, it will be experiencing a pseudo force which would be in this direction, that is ma. Okay, so if we are interested in finding out the direction of net force, okay, we can resolve, we will be using the component method in order to do that. So if we want to find out how much angle it is making with the incline, we need to resolve it along the incline and perpendicular to incline. And if we are interested in finding out what would be the open surface making an angle with the horizontal, then we should resolve it along the horizontal and perpendicular to horizontal. So let's say here we are interested in finding out how much is the open surface of liquid is making an angle with the uh, inclined direction. Okay, so here I will be resolving this mg. So let's say this angle here is theta, so this angle will be turn out to be theta as well. Okay, so this is going to be mg cos theta, and this is going to be some mg sine theta. Okay, so effectively, if we redraw this diagram over here, the component of force perpendicular to incline is nothing but mg cos theta. And along the incline, whether it would be the force would be up the incline or down the incline, that will depend upon the magnitude of mg sine theta and ma. So for, let's say, at this instant, like here, let's say the values are such that um, you can say that mg sine theta is greater than ma. So in that case, what we will be having, like this component, or let's draw a smaller line here because we are subtracting. So this would be simply something called something like mg m times g sine theta minus a, you can say. So the resultant direction, now you realize, so the resultant direction is going to be, this is going to be m times g effective. And so if this is inclined, okay, so the perpendicular to this line over here, perpendicular to this line over here, we will be having open surface of liquid. So this angle basically is 90 degree. Okay, so basically we are looking for this angle, say alpha, the angle the open surface is making with the inclined direction, or this angle alpha we are looking at. So geometrically you can very well see that this angle here is this angle alpha in this triangle. Okay, so geometrically it is very easy for us to find out the value of tan alpha, which is nothing but that would be g sine theta minus a divided by g cos theta. So let's look at some another diagram. In that case, we might be having ma might be greater than mg sine theta. So let's look at that diagram. So this is the inclined direction, this is the direction perpendicular to incline. So let's say this is mg cos theta, and if ma is greater than mg sine theta, this would be m times a minus g sine theta. Okay, and the resultant would be in this direction. Okay, so this is mg effective. So in that case, this would be the perpendicular, and this angle alpha, or this angle alpha we are looking at, so which would be going to be this. So alpha, again this time tan alpha, we could write it as a minus g sine theta divided by g cos theta. So let's look in this diagram. Okay, so if the inclination is like this, inclination of open surface is like this. Okay, so we can simply say like this belongs to when a is greater than g sine theta, and if inclination is like this, so this criteria belong to A less than g sine theta. We can have another situation when this body would be accelerating, this container would be accelerating up the incline. Let's have this case very quickly. Sorry. So this is the incline, and this is the container which is accelerating up the incline. So if we choose a particle, so along the incline, perpendicular to incline, so you must very clearly say that this would be mg cos theta, and this is going to be uh, or simply other way round. The pseudo force will be down the incline over here, so that would be this time m times g sine theta plus a over here. So this would be mg effective. So now we are looking at basically a direction perpendicular to g effective. So this would be something like this. Okay, so this here would be alpha, or this here would be alpha, or this here would be alpha, and alpha, tan alpha you can say, that would be g sine theta plus a divided by g cos theta. So in this case, the orientation would be looking like, so the reference line if we draw, so let's say this is the incline and this is the horizontal. So this reference line here, the open surface of the liquid is going to be something like this. Okay, it would be making some angle with the horizontal as well. So we can very well see, like, can we have a situation when we will be having like the open surface will be uh, along the incline, that means alpha is equal to 0. So that is definitely the case. For alpha is equal to 0 in this relationship or in this relationship, okay, what we can use is g sine theta. If it turns out to be equal to a, okay, then alpha is going to be 0. So if this container is sliding freely, then its acceleration down the incline is going to be g sine theta. So in that case, like if this is the container and this is the incline, so this is how the level of liquid, the open surface of the liquid, is going to be along the incline. So I think we have completed this discussion. More problem solving might be required for practice. Okay, so here we have exhausted our time. So let's say goodbye to each other, and thank you very much for joining.